So section 8.2 works on something called integration by parts. It's, as I said earlier, it's the closest you can get to kind of a product rule for integrals. You can't take the integral of a product as a product of the integrals, but there is something that's kind of close, and that's this here. Now I'm going to give you what's called a heuristic demonstration. That is, it's something that would inspire belief, but I think most mathematicians would scoff at this and not really regard it as a proof of the method. But it's good enough for our purposes to give you a little guidance or intuition as to what's going on here. So first thing first, I'm going to apply the product rule to these two terms. So you got the derivative of u times v. So u times the derivative of v plus v times the derivative of u. You can, of course, write that in any order that you want. Now, when you differentiate something, the opposite of differentiation is what operation? Integration. So if I integrated those things there, these two operations are going to cancel each other out. So I'll be left with u times v. And I'm going to write this term another way right here. I'll write that as u times v prime dx. And right here, I'll write this as v times u prime dx. So just kind of mixing it up a little bit. And let's see, I'm going to relabel this using different notation. You can do a U substitution. So let me call that the integral of u dv plus the integral of v du. And finally, I'm going to move this term to the other side. So u times v minus the integral of u times dv equals the integral of v du. And this weird concoction down here is where maybe you should start taking notes, because it's this identity that we're going to use to try and separate things and integrate them. And what that's going to involve is identifying a v term and a du term, and then trying to fill in these. And what we're hoping is that this integral, for some reason, is going to be easier to work with than one of the integrals we started out with. Now, it looks kind of strange, and it's going to take a little bit of getting used to, but in the end, it does work. Now, one thing that you want to keep in mind is that we're going to be differentiating our v term, and your choice for v is going to be something that is going to get easier or simpler when you differentiate it. And your choice for du, because we're eventually going to have to integrate that, hopefully that's something that you can integrate. It's not too hard to integrate. Certainly this method is going to take a lot of practice. So let's get going with problem number 16 here. The integral of x to the fifth ln of 3x dx. And when you do integration by parts, and you'll see me do this myself, you're going to have to label a few things. You're going to have to identify what u is, and excuse me, let's see, I want u and dv. So u is going to get differentiated, v is going to get integrated. So u is going to be equal to something that when you differentiate it, hopefully it gets easier. That'll give me my du. And here, with my dv, I'm going to be integrating that. So something that's going to get easier when I differentiate it is going to be the ln of 3x term. What happens when I differentiate ln of 3x? 1 over 3x times 3, so just 1 over x. Now, if I've used up my ln of 3x, the rest of it is going to be my dv term. So hopefully that's something I can integrate, and I'm pretty confident I think I can. X to the fifth dx integrates to x to the 6 over 6. Okay. By the way, there's also a dx term here. Now, accordingly, I've got everything I need because I've got u, v, du, and dv. I've got all four of the parts of this equation. So let's see if we can't piece together these parts. So it's going to be u times v, so it's this little cross product here, ln of 3x times x to the 6 over 6 minus the integral of v, or excuse me, u dv. You know what? I think I should move the other one over there. Yeah. Let's apply a little Photoshop here real quick. Sorry about that. So v du and u dv. My apologies to my old Calc 3 instructor. He gave me a mnemonic that I'm not going to tell you on camera, but if you want to catch me between classes, maybe I'll share that with you. All right, so I want v du. So v is x to the 6 over 6. Du is 1 over x dx. So notice what works out nice about that, right? We're going to get some nice cancellation here with the x to the 6 and the x. So that's ln of 3x x to the 6 over 6 minus 1/6 the integral of x to the 5th dx. And that was our objective. We were hoping for something that was going to be easier to work with for this v du part. So ln of 3x times x to the 6 over 6 minus 1 over 6 times x to the 6 over 6 plus c. And of course, that's a 36. So, and you can clean it up a lot from here if you wanted to, pulling out 1/6 or something like that. I'm not concerned about that. I'm concerned about you getting the integration by parts stuff straight. So the rest of this is just window dressing. So it's a nice trick, and it works. It greatly expands the amount of things that you can integrate. Like I said, one of the things that's kind of a clue for you in terms of what you want to choose as your u term is something that gets easier to work with when you differentiate it. Also, you got to keep in mind that whatever's left for your dv term, you have to be able to integrate. If you can't integrate it, then it does no good as your dv term. So there is one secret to being really good at these things. Do you know what it is? Practice. Yeah. Yeah. The enthusiasm on your face with it. Practice. All right. Yeah, I mean, there's just no substitute for it. It takes a while. If you'd chosen this for your dv term, it'd be a lot harder, and it probably wouldn't work, mostly because it'd be a challenge to do the integration of the ln term. I mean, it can integrate, but actually, and ironically, the integration of ln of x actually does require integration by parts. So to integrate ln of x, you need integration by parts. Actually, let's do it. Why not? Let's do it real quick. Because it does show you kind of a cutesy little trick about integration by parts. So if I had integral of ln of x dx, and I started looking at it going, I don't know, what's the antiderivative of ln of x dx? I don't know. So I want a u and a dv, a du and a v. So my u part needs to be something that I can differentiate, and it gets easier. So, well, there's not a whole lot of things that I can differentiate in this integral, so let's choose u is equal to ln of x. Du would be what? 1 over x dx. Remember, you get that dx term if you're being really careful here. What's left? Dx. So dx becomes my dv. Okay. And it almost feels like cheating. It's like, wait a minute, you can do that? And the answer is yeah, you can do that. Help me out here. What would be the integral of dx? X. All right, so remember it's u times v minus integral of v du. So how would that look then? It's going to be x ln of x minus integral of v du, 1 over x times x dx. So x ln of x minus integral of dx is x ln of x. Integral of 1 is just x plus your constant. So, like I said, ironically, you would need integration by parts again if you're going to choose ln of 3x to be your dv term. It would be a lot of work. So it's a good question, though, and I'm happy to show you one of these in which you're going to let your dv equal dx. And that's a trick that does come up from time to time. It's a good one, though. Okay, appreciate the question, Noor. Let's try another one, unless there's some more questions on this. Let's try problem number 12. The integral of 5x over e to the 2x dx. Well, let me start out by suggesting this: 5x e to the negative 2x, and it, maybe help out a little bit. First things first, always look for a simple U substitution. I'll probably throw in 1, maybe 2 on the next exam, where all you need is just a regular U substitution. All right, you don't have to do it by integration by parts if it's not really required. I'm not going to give you bonus points if you do it the hard way when there was an easier way. Okay, if you do it the hard way and you get it right, hey, that's fine. But look to do it the easiest way possible. If there's just a plain old U substitution, great. If this was a squared term here, you could probably get away with a U substitution, because the derivative of a squared term would be that linear term here, would be all set. But there's not. So, in as much as this is section 8.2, integration by parts, maybe we'll start thinking about integration by parts. U and dv. My message to you in this has always been, your choice for U is something that's going to get simpler when you differentiate it. And then what's left over, the dv, has to be something you can integrate. So, is there a part of this integral, Trevon? Yep, perfect. If we let u equal to 5x, du is going to be 5 dx. And that's cool. That's simpler, right? So hopefully when we put this together and form our v du term, that we'll get something easier to integrate. How about dv? Well, dv is going to be whatever is left over, and that's going to be this part right here, e to the negative 2x dx. Now, if you're being really, really formal, or maybe you're learning this just the first time in Calc 1, integrating that would require a U substitution. I don't like to get slowed down by a U substitution to try and do this little part of a bigger problem. So what I would encourage you to do is be able to figure out this in your head. The way I do it, what works for me, and you're free to find something else, is this. I know that integration is the opposite of differentiation. But let me first think about differentiating this. When you differentiate this, differentiate e to some power, It's going to be e to that power times the derivative of that power. What's the derivative of negative 2x? Negative 2. So if I were to differentiate this, I end up multiplying by negative 2, right? But we're integrating it. So the opposite of multiplying by negative 2 would be to divide by negative 2. Done. So our integral is e to the negative 2x over negative 2. And that's it. So if that works for you, great. If not, maybe you have to slow it down even more and do it out kind of longhand. But we've got all the pieces now. Let me rewrite that as negative e to the negative 2x over 2. So put that negative out front, sort of. So u times v is going to be 5x times negative e to the negative 2x over 2 minus the integral of v du. So let me be careful with that negative, because you're subtracting the integral, and I've also got another negative here. So minus the integral of e to the negative 2x over 2 times 5 dx. So maybe a little bit of cleaning up before you integrate. Probably not a bad idea. I can take out the constants of a negative and a half and a 5 and get, let's see, let's take out this negative as well. I'll put that all the way out front. So negative 5x e to the negative 2x over 2 plus 5 halves times the integral of e to the negative 2x dx. Well, we've kind of already integrated this one, right? It's just repeating this process. So it's negative 5x e to the negative 2x over 2 plus 5 halves times negative e to the negative 2x over 2 plus your constant. Again, I'm not going to ask for it to be much more cleaned up than this, although it's not a bad habit to try and clean this up. I'm pretty sure that the book would factor out some common factors like the negative, the 5, and the 2. So negative 5 halves. They'd also factor out the common factor of e to the negative 2x. That would leave behind an x. Let's see, the sign here would be it be a minus? No, it'd be a plus. X plus 1/2 plus a constant. So, I mean, it's nice if you can do that, and probably be easier for you to check some of your answers in the back of the book if you can. That's not the critical part. The critical part is getting past the integration by parts, getting to right here. All right, is there something that I might have gone over a little bit too fast that you need a little bit more help on? Slow it down here or there, someplace? Vicky, okay with that? Okay, all right. Okay. Let me show you a little bit of a shortcut to these types of problems for a certain class of integration by part integrals. It's called the table method. So the first couple examples are kind of garden variety examples of integration by parts. But in certain circumstances, when you have a polynomial term, you can kind of take a little bit of shortcut. So it's called the table method. So we're going to do the table method and then solve for the integral. Will be the two other types of integrals that we'll face here. And we'll start with problem 52-ish. So, or 52 prime. I'm going to change things up a little bit here. And the change is going to be, we're going to put a fourth power here, x to the fourth. Now problems like this, where you have x to some power and a sine or a cosine, are perfect for the table method. Or another one would be x to some power and an e to the x term here. Again, that'd be a good one for the table method. You can kind of imagine working on this by integration by parts. You'd say, all right, well, let's let u equal my x to the fourth term, and that means my dv term is cosine of 2x dx. So I have to repeatedly integrate this one. But after I differentiate it and I form up my next integral, then I'll have an x to the third term. I'll have to do this integration by process yet again. An x to the second, an x, and then a constant, and then finally 0. Wow. It could take a really long time. It could ruin your weekend. So let's take a shortcut here. Let's do all the derivatives right at once and all the integrals right at once. So the derivatives would be 4x cubed, 12x squared, 24x, 24, and finally 0. And that's a good place to stop. That's also why you would want to let u equal a polynomial term and not something like e to the x or cosine of x. Because when you differentiate a polynomial term, eventually you're going to get down to 0. It's not going to happen with sine or cosine or e to the x. You want something that's going to differentiate eventually away. Now, with these, I got to do repeated integrations. And so we're going to have to think carefully about that. So, what do you get when you integrate cosine? Sine. So it's going to be sine of 2x. But what about the constant here? Because I got a 2x in here, there's got to be a constant in there somewhere. A 1/2, right? Because if you were to differentiate this, you'd end up multiplying by 2. But because we're integrating it, we'll end up dividing by 2. So let's just put that 1/2 out in front here and keep going. We're going to need to keep going down to this level right here, down till we're even with the zeros. So what's the next one? Negative of cosine of 2x, good. What constant's out in front now? 1/4. Good, let's keep going. When you integrate cosine, you're going to get sine of 2x. Is that going to be a positive or negative? Yeah. Well, when you integrate cosine, you get sine. But out front, what's going to be out front now? Negative 1/8. Good. And I need 2 more. See if you can't figure those out. Figure out what those next 2 are. Because this is going to be one of the challenges that you're going to face in working with this integration by parts. So figure out those next 2. Delane. So I see the pattern here so far. It's sine, cosine, sine, cosine. So I put those next 2 here. But what we need to concentrate on is what happens to the coefficients here. So when I integrate here, what coefficient is going to come out in front? 1/16. Good. Notice that it becomes a positive 1/16 because the integral of sine is negative cosine. And that negative and this one will cancel. Thank you. How about the last one? Positive 1/32, right? Because the derivative of sine is cosine. You don't get that negative there. And conversely, when you integrate cosine, you get positive sine. All right, almost done. So there's one last little piece to all this, and that is I'm going to draw some lines here connecting these little parts of our table, and then we'll finish this off. So our lines are going to go here, and then here. Notice they're going kind of down one level, from upper left, up and left to lower right. There's one tiny last little thing that we need to take care of. That is, when we multiply these together, there's also a little sign game that we're going to have to play. And that sign game is this. This is going to be a plus, minus, plus, minus, plus. So when you multiply these together, it's this times a positive, this times a negative of this, etc. So let's see if we can't put all this together. It's going to be x times 1/2 sine of 2x. So we'll call it x to the 4th. I think I said x. X to the 4th times this. X to the 4th over 2 sine of 2x. This times this times this. Well, the two minuses cancel each other out, don't they? Now, how much detail do you want me to put in? You want me to just write 4x times the 1/4, or can I cancel the 4's right away? Cancel the 4's. All right, so it's going to leave me with a plus x cubed cosine of 2x. The 8 and the 12 will cancel out a 4, and I've got a minus times a plus, so it's going to be a minus 3/2 x squared times sine of 2x. Again, some more cancellation. This time I can cancel out an 8, so it'll leave me with another 3/2. And again, it's going to be a minus 3/2 x times cosine of 2x. And deep breath, get the oxygen bottle, almost done. 24 over 32. Cancel out the 8, so 3/4 sine of 2x. And just when you think you're all done, you forget something. Constant. Don't forget that constant. All right. Whew. But, yeah, that's the answer. That's it. All done. I tell you what, it's a lot cleaner than doing integration by parts like 5 times. That'd be a real nightmare. I think I did it out one time for a different problem, just to see what it was like, and it took up an entire sheet of paper, writing as small as I could. It was a pain, and I kept on having to go back and fix signs. It was a pain. This is so much nicer, this little table method. So look for it, look for using it when you have, x to some power times cosine sine or e to the x. We'll do another one like that in just a second. Before I give you problem number 50, anything on problem 52 here?
Does it always go plus minus?
Yes, it always goes plus minus, and it starts with a plus.
Okay.
Yes. Liam? Okay. Yes. Yeah. When do you not use it? If you only need to do this once, I'm not sure I'd bother doing it. I mean, you could. If you had just an x here, then it's just a regular integration by parts. But it would actually work even if this was x to the 1st power. Where you would not use it is if you didn't have something quite so neat that would differentiate away to 0. That'd be probably one place that you might not use it. But for problems like this, it works out pretty good. So let me give you another one like that. It's problem number 50, and I'll let you try this one. The integral of x cubed e to the negative 2x dx. So start out by figuring out what you're going to let u equal and dv. and work it down from there. wings, they could fly.
No, we're just not playing good teams.
That's.
Like the Browns,
But it's the Lions, man. They could play. They could probably
now.
beat the Patriots, but then they lose to like the Browns. You know.
Patriots just lost on Sunday too.
Yeah, I
Cowboys.
saw that. Cowboys.
All good.
All right, I'm not drinking the Kool-Aid yet. All right. Sorry. All right, so let's see here. We're gonna let this be our U term. This is our dv term. We got all the derivatives and all the integrals. Hopefully you get good at doing this integration in your head. It's going to save you a lot of time if you can. Plus, minus, and then it's just a lot of products here. So we end up with minus x cubed over 2 e to the negative 2x. A minus and a minus is still another minus, so minus 3x squared over 4 e to the negative 2x. A little cancellation here. Another minus, we'll end up with a minus 3/4 x e to the negative 2x. And the last one, all these negative? Yeah, I guess so, huh? Negative 3/8 in lowest terms, e to the negative 2x, plus your constant. Yay! Okay. You know, like I said, in the book or your answer key, they'll probably factor out negative e to the negative 2x and leave behind x cubed over 2 plus 3x squared over 4 plus 3x over 4 plus 3/8 plus your constant. Either one of these is fine. I'm quite happy with that one there. 6/8 are reduced, or always, yeah. Any other comments? Yes. It didn't really come out of the constant. You could put the constant in or out. It doesn't matter. Yeah. So sure, it's technically it's a different constant at that point, but it's still a constant. Yeah. Yes.
Can you move her back up to
Sure.
How do you get yours? Do we just multiply?
Well, it's this times, this is either a factor of +1 or -1. And it's going to multiply, you know, this times this all the way along. So that factor of a plus or a negative is going to adjust the sign of your product. And that's true when you're doing the table method. If you actually laid it out and did repeated integration by parts, what you would see is that after you do the first one, if you do that again, you'll end up distributing a negative sign, which is why those negative signs kind of cancel and alternate like that. All right, appreciate the question. Anything else on that one? Yes. X to an integer power, something that will eventually differentiate down to 0. That's what you're looking for.
So if we did it for the problems we did earlier?
You know, I typically think of using it when I have an x to the n power in the integrand, but what's that? No, I'm not going to tell you this is what you have to use here. So that's something you're going to have to kind of work out for yourself, how you want to do it. Part of that is because some of these problems you can do different ways too. So if you see something, oh, gee, I can do it with just a U substitution, hey, go ahead. Okay, let's try problem number 42. So we're going to do a couple that involve some definite integrals. So 0 to pi of x sine of 2x dx. Now I'm going to do two problems kind of like this one in 48. One I'll do with the table method, one I won't. Let me go back to doing just kind of a regular U du kind of problem here. So I need U and dv. Here's du and here's v. Any suggestions for u? X. Because when I differentiate x, I'll get a dx term. So that leaves my dv has to be everything else. That's the sine of x, sine of 2x, I should say. Sine of 2x dx. So the big question then for Donnie is, what do I get when I integrate that? What's the antiderivative here? Yeah. Negative cosine of 2x over 2. Nice. So remember, I got to fit that into the formula u times v minus the integral of v du. And I think I've got everything I need. So my u times v, I'll take the 1/2 out front. So negative 1/2 x cosine of 2x minus the integral of v du. And let's be careful here because I've got a negative that requires a little bit of extra care. V du. I'd probably suggest that we factor out the negative 1/2 and clean this up a little bit. So negative 1/2 x cosine of 2x plus 1/2 times the integral of cosine of 2x dx. Minus 1/2 x cosine of 2x plus, that's going to be 1/4. 1/4 of what? Sine of 2x. Now, if this were truly an indefinite integral, I'd need the plus c. But if you remember, at the very beginning of this started out as a definite integral. I kind of left off the definite integral part until we got all the way down here where we have to do our substitution. We have to substitute in limits and then finish this off. So I guess technically I could put a little bar here and then limits here and limits on the bar, etc. But I don't know. My laziness is to just do it when I'm all set. So let's put in the upper limit. That's going to be minus pi over 2 times cosine of 2 pi plus 1/4 sine of 2 pi minus 0 plus 1/4 sine of 0. And happily for us, the second part disappears completely. That's just a 0. Do I get any other simplification? The answer is yes. What's the sine of 2 pi? 0. 2 pi and 0 are essentially the same point, and the y-coordinate there is 0, so that's a 0. Almost done. What about cosine of 2 pi? It's just 1. So what I end up with is negative pi over 2. How are we looking on number 42? Please. Well, all right. If you did u equals 2x, what would be the derivative of 2x? Just 2, yeah. So if this was an x squared, then you could do a regular U substitution. But here, we're not quite so lucky. But appreciate the question. Any other questions on this one. Okay. One thing that kind of bothered me about this one is that I got a negative answer. So what's that mean about the graph? What's that saying should be happening with the graph? Yeah, it's below the x-axis, or most of it's below the x-axis. So in this particular case, if you graph this, you can see you got an area above, but most of the area is below. So on balance, it cancels out and gives you a negative value here. So, okay. In fact, let's play around and do one more thing here. We'll integrate from 0 to pi and see what we get. Ooh, ah. Cool. And if you recognize that number, negative 1.5707, etc., that's pi over 2. So a nice confirmation that we got it right. Okay, as promised, problem number 48. So the integral from 0 to pi over 8 of x times secant squared of 2x dx. Now I made a promise to you that on this one, even though it's not what I typically think of as the table method, let's do the table method just to see what it looks like. All right? I have somebody that forced almost every single problem that they could into the table method. It was crazy. They made it work, but it seemed like more work than it was worth. Okay, so if we're going to do the table method here, then I need to know what u is and dv. So start us off. What's u equal to? X. And then dv's got to be kind of like everything else. So du would equal 1, and then the derivative of that is 0. Okay. How about the next one here? It's going to be a 1/2 tangent of 2x, or you can do a tangent 2x over 2. That works out good too. All right, we need one more there. All right, good. 1/4 of what? It's cosine, I think. Minus natural log of the cosine of 2x. So, all right, I guess I made it work. Let's line some things up now. So our table's kind of short. Got a plus and a minus, or you can consider it a +1 and a -1. So that when we multiply these factors together, they line up in terms of their signs. So I'll get x over 2 tangent of 2x minus, and a minus is going to be a plus. 1/4 the ln of cosine of 2x. And I'm not going to bother to put a constant here. Why not? It's a definite integral. So 0 to pi over 8. Wow. Have fun with that one. Let's take a break here, and I'll let you guys work on it. And All right. So let's see. Let's put in pi over 8 divided by 2, tangent of 2 times pi over 8 plus 1/4 the ln of cosine of 2 times pi over 8 minus, and I think when we put in the lower limit, thankfully everything's going to be 0. I'll get 0 times 0, which is 0, plus 1/4. What's the cosine of 0? 1. But the log of 1 is 0. Yay, that second term cancels. So that's pi over 16 times the tangent of pi over 4. But the tangent of pi over 4 works out pretty nice. Anyone? Tangent of pi over 4? 1. It's just 1. Plus cosine of pi over 4 is root 2 over 2. Yeah, I'm not sure it's going to really simplify it to anything nice. 1/4 of the ln of the square root of 2 over 2. I'll just leave it like that. That's good enough. I'm sure you can probably get creative and fuss with it somehow, but I just don't see that it's worth it. It depends, unless I say, finish it with fn int, then I am looking for an exact value. But I tried to be reasonable on the last exam. I didn't make you do out every single one to the nth degree. I threw in a few fn ints, and I'll be doing the same thing on all our exams, really. Pi over 2? Or pi over 4? That's a 16, sorry. Sorry about that. Thanks for the... Yes? Here? Oh, 2 and 8 cancel?
Right where it says equals pi over 4 plus 1/4.
Oh, you know what? It should be 16. My bad. Thank you. So it should be 16. Thank you. Anything else here? Someone else want to make me look bad for the video? Just kidding. All right. I think this is a good place to take a break. There's 1 or 2 more that I want to do, including a fairly long one, which is a solve for the integral. And maybe I'll give you a chance to work on a couple on your own. Let's take a break here, so we'll do this video in 2 parts.